Okay, so now I want to prove another inequality involving real numbers. We'll actually use what we did before a little bit. But this time I'm going to prove an inequality that I don't think you've seen before. It's called the algebraic mean geometric mean inequality. And so let me state the theorem. Okay, so this is theorem 1, and I'm going to abbreviate this algebraic mean geometric mean inequality. Okay, so here's the statement. So if x and y are real numbers, again, they need to be positive because, again, we're going to take square roots. Then the inequality is as follows. If you take the square root of the product of x and y, that will always be less than the sum of x and y, which, sorry, the sum of x and y divided by 2, which the one on the left, the one on the right is what we call the algebraic mean, or sometimes we just call it the average. So this is what's called the algebraic mean in this inequality. But on the left, we call this the geometric mean. Now, most likely, you haven't really seen the geometric mean before because it's not as common. In statistics, we use the algebraic mean or the average, right? So, but let me just remind you of how these two things work sort of intuitively, right? So for the average, this is something you're already mostly familiar with, but I can just draw a simple picture. If I just take x on the number line, let's say this represents x, and then y maybe is bigger, then the average, right, would be somewhere, would be halfway in between here. So maybe, let me do this in red. So maybe the average is like right here, which is where you take x plus y and divide by 2. So we take the total length, divide by 2, and I get halfway, which is somehow the average of x and y, right? Okay, so that's something you're usually already familiar with. In the geometric mean, you might wonder, why is it called geometric, right? So now let me draw a different picture. So let's say this side is x, and this side is y, roughly the same sides as we used before. Now let me form a rectangle, and let's say this rectangle has area A. Okay, now when I go to do the geometric mean, it's like I want to take a square whose area is the same as the rectangle I just drew. And I'm not going to claim that my picture is perfectly accurate here, but the point is there should be some square. So a square has to have the same side lengths here. So they're both side length x, y. Notice the area over here is the square root of x times y squared, which of course is x times y, and the area here is literally just x times y. So the point is they have the same area, but in some sense I call it a mean or an average because now I've formed it into a square. I forced both sides to be the same. Okay, and so that just gives you some visual interpretation of algebraic mean and geometric mean. And what makes the inequality interesting is that apparently, no matter what, if you take two non-negative numbers, the geometric mean will always be smaller than the algebraic mean. Okay, and just want to mention, I'm not going to make a big connection with this, but if you've seen linear algebra before, or when you see linear algebra in the future, this will be related to the determinant, which is what you see on the left if it's a if it's a small matrix, and the trace. Okay, so there are more advanced version of this algebraic geometric mean inequality involving the determinant and the trace, and involving more than just two real numbers, and so on and so forth. But right now, we just want to prove this version of the algebraic to geometric mean inequality. All right, well, let's also play with some examples, since presumably this is a new inequality for you, and so there's no reason why you should just believe it. So let's see what happens if we play around a little bit. So let's see what happens if we consider x equals 4 and y equals 25. Okay, so the geometric mean then is like 4 times 25, which of course is 100. So that gives the geometric mean to be 10. And the algebraic mean is like 29 over 2, and that's 14 and a half. Okay, that doesn't prove anything, but it's sort of nice to play around a little bit and see that it works here. And it might be interesting just to think about what happens if x and y are the same number. So if x and y are both 10, what happens in this inequality? So then I take the square root of 10 squared, which is the square root of 100. And here I take 10 plus 10 all over 2. So that's, of course, 10. And so we might start to conjecture, and actually, if you think about it, it makes sense that if x and y are equal, then both sides of the inequality are equal. So it's interesting when you have an inequality to try to understand what makes both sides of the inequality equal. So in this case, we can already notice that if x equals y, then square root of x times y is equal to x plus y over 2. So there's like no gap in the inequality. And that's because, of course, the square root of x squared is just x, and x plus x over 2 is equal to x. Okay, that's not a proof, right? That's just us playing around. Again, I want you to get used to playing with things because that's how you gain understanding and comfortability with the statement. None of this playing is proof, but we can't just go right into proving something if we don't feel comfortable with the expression itself. So we're just playing around. And it is nice to characterize the case of equality in an inequality. So great. Let's go into a proof sketch, though, and try to play around with what might work to actually prove this now. Okay, so proof sketch. Well, I can write down what I want. I can't, I mean, this is unfair in a proof itself, but let's write down what I want, and maybe I can rewrite it in an equivalent way. Okay, so maybe I don't like the square roots because it's hard to do algebra. So let's just square both sides. So let's square both sides. If I square both sides, I get rid of the square root on the left. And of course, on the right, I have a little bit of work to do. And I get x squared plus 2xy all over 4. Okay, good. Now, if I multiply both sides by 4, I get 4xy less than x squared plus 2xy plus y squared. Now I see several terms involving x times y, so I want to move them all to move this 4xy to the right-hand side. Get 0 is less than. And now I can factor the right-hand side. So when I factor the right-hand side, I get x minus y squared. Okay, now we have to be careful because I'm playing around here. I started with what I need to show. So this is a little unfair. I started with what I need to show, and I played and played and played, and now I showed that it's equivalent to, so let's just note what we want to show is equivalent to x minus y squared is positive. Now, the point is, though, that showing x minus y squared is positive, is non-negative, is actually something I can just pull out of a hat and claim, because I know when I square anything, any real number, I get something negative. So notice for any x and y, the real numbers, we know that x minus y squared is positive. Okay, so this sketch has led me to something that I feel good about because I can't claim the conclusion right away. That's where the sketch is not quite going to work. If I just said start with the conclusion, like that doesn't work, right? Can't do that. That's the thing I'm trying to show. But what I notice now is I can right away say if you square any real number, you get something non-negative. That's just how real numbers work when you square them. So when I actually go to write the proof, I'm actually going to write this in the opposite order. I'm going to start with this claim that I can make without justification because anything squared is non-negative. And I'm going to show the reader that that claim implies what I want, right? So I'm going to go backwards through this logic. Okay, so we're ready to start the proof. So now that we have the idea, let's start the proof. Okay, so proof. Assume x and y are real numbers and x and y are positive. Remember, the x and y being positive are just so that we can take square roots of them. So that will come up at the very end. But for this first fact, then, since any real number squared is non-negative. By the way, this non-negative word is when we want to include the possibility that it could be zero. Positive usually means that it can't be zero. So we're just saying that since any real number squared is non-negative, we know that x minus y, which is itself a real number squared, is non-negative. Okay, by expanding the left-hand side, we find, okay, so now when I expand the left-hand side, I get x squared minus 2xy plus y squared is bigger than equal to 0. Okay, now because of our sketch, we know that we want to have a 4xy on the right-hand side. And so we're going to add 4xy to both sides. But notice the reader is not exactly sure why we're doing that at this point, right? But anyway, that's okay. They'll eventually realize why. So by adding 4xy to both sides, we find. By the way, though, this is important to when you're reading proofs. Remember that when you're reading a proof, whoever wrote the proof did their own scratch work, but they're not showing you their scratch work. So sometimes a step will seem like it comes out of thin air for you, the reader, but you should always remember that this person didn't just come up with this out of nowhere. They did some kind of scratch work. They did some kind of exploration and saw that this would work, right? So similarly here. So if we add 4xy to both sides, we get x squared plus 2xy plus y squared is bigger than 4xy. Good. So by factoring the left-hand side, we find that we get x plus y squared now. And now we can take square roots. We find x plus y is bigger than or equal to 2 times the square root of x, y. And now we just have to divide the 2 to the other side, right? So now by dividing both sides by 2, we get that x plus y divided by 2 is bigger than or equal to square root of x plus y, which was what wanted to show. So that's the end of the proof. Okay, very good. But be careful in a proof like this. The reason why this worked is because we were able to develop a condition, this one at the very beginning, which we could claim was true without having to uh, do anything fancy, right? So we started with something that we could just claim is true because it's a square of a real number. We know it's non-negative. And then we took that and expanded it out until it was equivalent to the inequality we wanted, right? But this only works because we were able to find a condition which we could just claim as a non-negative by some solid fact on the real numbers that we know. Okay. Also, I just want to mention that this proof right now, we're explaining every single algebraic step with a sentence. Eventually, you might omit some of this and make it simpler. But in this class, I want to show you how to write proofs quite carefully, and eventually, in a class, you might learn to abbreviate some of these steps when it's appropriate. But for now, we want to be very careful and write things out and explain things. And later on in different classes, you can learn which steps you might be able to skip from time to time. Okay.